Dear colleagues, I am very glad to be here at this conference. I thank you for the invitation, and I am from Odessa National Maritime University, Ukraine, Ivan Andronov, the head of the Department of Mathematics, Physics and Astronomy. So here you may see Odessa and also the logo of our university. So what I would like to speak about is on possibilities and fake discoveries which are often even being published, and thus just to show some errors and some methods which should be used. So there are some methods which we have developed, and in our opinion it is very important to have complementary methods which allow us to see what is the truth and to be best for different types of variability. And also there is, I will go fast here because it is recorded and so on. But I would like to start with some epigraph which was shocking to me, and even a quarter of century have passed, I may never forget it. So we no need for new methods for time series analysis, because even Ptolemaios knew the Fourier transform. Okay, so it was very funny. The paper was published in Astronomy and Astrophysics later on, but anyway, I will not forget this referee comment. Okay. We have many types of variability in variable stars. There are 73 types in the general catalog of variable stars, and 7 of them are presented here. So obviously it is not possible to use the same method for all these types of variability. Of course, we may use it, but it will be not effective for all of them. And the problem which we have that in our observations from ground-based observations, there are seasonal gaps, as is seen here. And even if we have space observations, the observations are not from minus infinity to plus infinity. So there are typical problems, and so this is why it is not recommended to use oversimplified methods, even if they are very popular. Last year, April last year, there was published a book on knowledge discovery in big data from astronomy and Earth observations, and there was a chapter written by myself on advanced time series and beyond the oversimplified methods. There are formulas and many examples which I will not show here. I will show other figures, not formulas, but just figures to see what is going on. In fact, this is a current list of my publications in the ADS, and so there are many, many applications. Of course, no time to show all of this. In fact, we work with the different countries and also have time series from these countries, from observations, and make analysis of them. And also we have organized an international collaboration on interlongitude astronomy on different types of objects to see that the observations may start in Japan, in Korea, in China, and then going to Europe, then to US, and so on. Okay, and you again may see the main methods which we develop for irregularly spaced data. Okay, so the basic equations are very well known, but sometimes they are forgotten, and people use oversimplified things for this. So there was some review, my first review maybe on this topic, and so we prefer to use complete mathematical models. So no pre-whitening, no detrending, but just make as complete as possible. In this case, there are no biases, and so the results may be statistically optimal. Okay, so very fast, just going to global and local approximations, and so the number of parameters which have to be used for good approximation. You may see here, for example, 13 parameters, and there are waves which are not real because there is an outburst and here is a constant. But okay, due to the limited number of parameters and the global model, we have the Gibbs phenomenon, which is in here. Also, we use not only least squares and the Fisher criterion for this, so which is called ANOVA, analysis of variances, but also have introduced different parameters. This means the mean accuracy of the approximation at the points, times of these observations. So you may see here that it has some minimum, and then with an increasing number of observations and parameters, we have here an increase. So there is a single minimum, which is very nice for this short sample. And for a long sample, you see that the minimum is not so well pronounced. But anyway, you have here 13 parameters and here only 4. So the difference is very nice. Also, as we work with variable stars and also with new discoveries of variable stars, it is interesting to see whether the star is variable, because sometimes the mean accuracy may be the best with a number of parameters, which is unity. It means a sample mean. But we want to look for variability. In this case, we introduce a parameter signal to noise, and maximum signal to noise may give us the statistically optimal number of parameters. Okay, here are the errors for different number of parameters. As you may see here, they are different from classical curves which may be seen in the university, because here we don't have the homogeneous regularly spaced data, and so it is slightly symmetrical because of asymmetry of the data. Of course, not only the polynomials or trigonometrical polynomials may be used, and so later on I will show a program which we have developed, and so this is all-in-one 21 method which is included in our single program. Okay, going back to the Fourier, just to see here classical formulas, and that here we have a constant step in time. And so everything is very good and very simple because we have restrictions on the data. And so you may see here the first type of fake discoveries which may be done. So here you see half of a sine function. So in fact, it will go down, and the period is twice larger than the interval of observations. These are model data, not real, but anyway, you may see that if we will use the Fourier transform, anything discrete Fourier transform, fast Fourier transform, and so on, you will see here a continuation, and so a duplication of the data here. And so the period which will be done by the Fourier transform, it will be not true. So the true period of this is twice larger. So this is something. And the amplitude diagram, periodogram, which is shown here, it has maximum at a wrong period. The true period or true frequency is shown here in green. Also, we have this typical situation also when we have not an integer number of cycles per period of observations. Again, these data, black data, are duplicated in violet, and so instead of having a true sinusoid, we have here a jump, and this jump makes a fake or wrong spectrum, because the spectrum will show a very slow decay, and we have here jumps. Okay, it is well known, but anyway, this is the situation which we see in our observations. Also, here you may see, for example, convergence of the data, a very fast convergence for asinusoidal data. So this may be typical for a pulsating star in intensities. Okay, here may be an asymmetry as well. But anyway, you see that the first sinusoid is bad, but even the second one is closer, closer, and closer. And what we have in our application of the fast Fourier transform, so here we have some data, and the rest should be replaced by any other signal. And so we may have some choice in making this signal for this data because the number is limited to 2.m. So here is 128 points, but if we have only 100, so we have again a wrong spectrum. You may see the difference here and here. The signal is the same, but we don't have exactly 2 in an integer power or points. Okay, and also here we may see the bias periods and so on. And so this is dependent on how the times are distributed. So by increasing number of times, we will seize the peaks, the wrong peaks here, and then you may see here only one peak. And the best choice in this is to have a random data. In this case, these errors are much smaller. This is why we have organized this project, which is called interlongitude astronomy. So we have different longitudes, different times, and so these peaks are seized very effectively. Okay. There are sometimes very strange approximations. For example, we see in ABSO that there may be trigonometrical polynomial, and it is difficult to see what is the error here and where is the minimum at this maximum and so on. But okay, such types of approximations are typically used. This is other example when we have observations with trend, and okay, we may get some formal approximation, which is very bad here. Again, looking for detrending, how detrending may give wrong results. So for example, we have here again half of the period model sinusoid or cosine function. And if we will remove the trend, linear trend as recommended by any textbook, then we have the residuals. And for these residuals, we may also obtain some periodogram, and this periodogram is definitely wrong. So you see here the difference between a true periodogram and this one. So if we just remove the trend, so it gives bias to your spectrum, to your periods, and this may be, you see here the peak and here the peak again, around twice. And we have developed a program which allows to use an algebraic polynomial of any order for trend, and then a trigonometrical polynomial, which may have also different order, a different number of harmonics, and then we may get periodograms and also the predictions. Here you may see plus minus 1 and 2 sigmas, which are seen here. And of course, you may see how it may be bad in this case. Now, again, the periodogram for some signal, just to see that we call it periodogram, so the function of the period. But in fact, we use frequency, and so for common methods, the width of the peaks is constant here in frequency, not in the period. And so here you may see that it is no unnecessary thing that to use period. However, there are some programs in the internet. Okay, we will use periods, not the frequencies, and so we'll get something like this. And the same curve, which is shown here, for the logarithmic scale, and so typically it is used for the wavelet transform and so on. And these different curves which are shown here, they correspond to different number of different degree of the trigonometric polynomial. So this is a simple sinusoid, and so there is plus harmonic and okay, 4 times the main frequency and 8 times. So you may see how it goes to these things. Also, the thing which I sometimes see and even criticize in my referee reports to the papers that, okay, there is a false alarm probability distribution. And so very nice that people want to get discoveries and say that the probability, say 5%, is at some level, and we have one or two or a few peaks which extend this. In fact, even Walker, more than 100 years ago, he had written this formula, and okay, the probability to have at least one peak at any frequency is very different from here. No, these are models, and so it is very nice to see these curves. Okay, so for multi-column viewer, it has a few possibilities also to increase the accuracy of CCD photometry by making an artificial comparison star, and contrary to the method of ensemble photometry, where by default the weights are better for bright stars, no, assuming the Poisson distribution. Here, bright stars may be variable as well. We may detect them, and this is also this one. Okay, the degree of trigonometric polynomial, again, for some real star, which is here. And so we see that we have somewhere to stop and to get the best approximation. Also, the problem is, especially for algos, that trigonometric polynomials, they need a very large number of parameters, and they show the Gibbs phenomenon. And so one may say, okay, pulsations or something like this. Again, this is a real star, a real example, and a different number of parameters used in the trigonometric polynomial here. And you may see that there is some peak. And for example, here we have to use 45. This is from ANOVA method or Fisher criterion, or 40 parameters, which is incredible. And so we proposed some special method with some pattern, and you see that it is 6 times better than the best trigonometric polynomial. You may see here that there is a trigonometric polynomial of power 2, which is very good for ellipsoidality and reflection effect in binary systems, but the minimum is seen here, and so we look for the profile and the borders here where the minimum or maximum is. And so there is some continuum which we may see here. And this is very different from example from this article when the minimum is approximated by a parabola with a fixed period. You see the quality of the same data using this method. But anyway, it was published, and some hundreds, thousands stars were done with this. So we have made some catalog of eclipsing binaries, and you may see that not only algos, but also EW systems are, they have this minimum, and so this method allows to distinguish these stars, for example, from elliptical ones. The next part, which is made in our group, is on variable stars, on pulsating variable stars, and also with changes of statistically optimal approximations during a century from the AVSO and French databases. The scalegram analysis is the next part which we use for aperiodic stars. And so we started with running parabola, and this is precursor is running mean, and in fact it is some even more aperiodic for wavelets. And so you may see that they are connected, and you may see in my review in this chapter as well. So we have some approximation, and we compare different points which are here at the center. And then there are statistical parameters. So there are some analogs for a periodogram, which we called scalegram analysis, and one may study aperiodic signals, quasi-periodic signals, even with very bad coherence. Okay, so the wavelet analysis also, it is very old paper, review paper by me, so it was published in Russian, but it was translated in English, so it is available, and so this is even in the Russian-speaking publications of wavelets, so it is listed here. Okay, number one, just because of alphabetical order. And also you may see here the difference which we have if we will use different decay constants. Typically in the Morley type wavelet, this one is used, but we may also choose this parameter to make statistically optimal approximations here. And if you will have very fast decay, so in fact it is goes to running parabolas asymptotically. So we prefer to use parabolas instead of sines and cosines with very small arguments. So you may see here the parameters. Again, I will not repeat the paper, that review which was given there. So you may see a periodic star. So there are outbursts which are not strictly periodic, but anyway, the wavelet analysis will give a changing period and also different parameters. And we use the parameter WWZ, which is the signal to noise analog for weighted filter function for the wavelet. And so we use the least square method. You may see here how it works for different parameters. And also we tried to study different test functions for the wavelet and to see which one has the best contrast. So you may see here from minimum to maximum. So here is true and here is some noise. And of course, WWZ is the best one. Other examples, so with changing periods, pulsating periods in variable stars, we see here. Also, there are problems that there may be large gaps here, and so, okay, you see here that no sense to approximate anything, and here is the wavelet skeleton, and so on. Okay, so our analysis even was published in the Rosat calendar, July 2006, as one of the nice figures for this. So for periodogram analysis, we use different things, and monitoring is very important because, okay, there are very short period stars, and so 100 rotations of the white dwarf per day, and so multiplied by 1 year, it makes very large gaps, and so sometimes it is difficult to understand what is going on. Next part, very short, so it's just to see that I have introduced that this program is all in one, and so there are 21 approximation in 11 types of functions, which was made by Katerina Andrich. You may see here an exoplanar transition and its approximation. So obviously we have to use some splines, and these splines may be non-polynomial, which are seen here. And so you may see examples, for example, asymptotic parabola. So by choosing the borders and then the approximation and its error estimates, which are here, again for the flat minimum, you see here. And so there are types of functions which are used. You may use all of them with automatically choosing the best one, or prefer some one function. And you may see here the direct links there. Okay, this is my site I have created then, and of course, a younger generation active girl has made much nicer curve, but with the same content. Okay, so these are results of approximations of pulsating stars using these programs and so on. Comparison of different approximations here. So you may see how it is different. Other example is a rare Lyra type star with the Blaschke effect. So in fact, we have very nice curves, and now we have discovered many such objects from the TESS observations here. Running sign, so this is the method which I prefer instead of the wavelet for the signals which have relatively good coherence. Here, for example, the period changes twice. This is a stress test for this function, and you may see that the periodogram has no sense. So these are from 50 to 100 units changes the period, and there are some peaks which correspond to nothing. And if we will use O minus C diagram or phase diagram, only at the borders you have some deviation from the theoretical value. Now, okay, there are some applications for different stars. You see here that some may be constant and then go to very large amplitudes here. Now, again, this is for the wavelet with different decay constants, and the periodogram here is seen as well. So the periodograms and very large sample of curves which are used. So finalizing, I would like to say that we work with our own monitoring and also with different countries who send us observations, and so we analyze them and so on. And of course, we use sometimes curves from the published data which are ground-based or space. And so we want to have a complementary set of methods, not just a Fourier transform or something like this, or a polynomial one, which is included in the electronic tables. So we make special shapes, special patterns for this, and so this expert system will produce the same results only if we have a pure sinusoid, and so the sinusoid has an integer number of periods per duration of observations. And of course, as usual, I show my chief, well-known specialist in astrophysics of variable stars, and so I am thankful to him for the start of my career. So I'm very thankful to you for your attention, and so I wish you all the best, and thank you again for the invitation and for attention.